Hello everyone, welcome to another episode of Noir Letters. This is your host Mahmoud Noir. Today we'll be talking about waves, what makes waves, type of waves, energies associated with it, etc. etc. Please leave any comments for any topics you want me to cover or any suggestions, and don't forget to like, share, and subscribe. And shall we get started? So, sinusoidal waves can be either transverse or longitudinal. They can be individual particles that oscillate back and forth with displacement patterns. So there are two types, transverse waves and longitudinal waves. Okay, so transverse waves are the direction of particles oscillating perpendicularly to the propagation. They're basically like waves, like electromagnetic waves. These are wavelengths, it's like they go up, down, and up and down, up and down, up and down, like a normal wave is. Alright, and then you have longitudinal waves, and these look like kind of lined up sticks. Alright, they are parallel to the propagation in which the energy is transferred, such as sound waves. So you got transverse waves. For instance, these can also be like light waves, for instance, alright, and as well as sound waves, alright. Longitudinal waves are more like parallel waves and related more to sound waves. Next, you have the speed of the wave. So the speed of the wave is basically frequency times wavelength. And in order to measure a wavelength, it's basically from one end of the crescent to the other end, and that's a successful wavelength. Alright, so a period is the time it takes for two successive crescents, so one wavelength. So that's a period. That's here how to calculate a period. Alright, and in order to calculate it, it's equal t is equal to 1 divided frequency, or frequency is equal 1 divided t if you want to know the frequency from it, if you get a question like that. There's time equal 1 divided, for the period is 1 divided frequency. Then you have angular frequency, which is represented by this. It's equal to 2 pi frequency, or 2 pi divided t. And it measures how quickly an object or a system is rotating or oscillating. So it really measures how quick, or the speed of the object oscillating or rotating. And next we have the principle of superposition. When waves interact together, displacement of the resultant wave at any point is equal to some displacement of two interacting waves. So that means that you have two waves, they could be the same frequency, different frequency, and they come together. They can either add up and make a bigger wave, or destruct and have no wave. So there are two types, constructive interference and destructive. So I want to explain principle of superimpose more, or like principle of superposition. And if they meet at different phases, like I said, they may interact destructively, or they can result in a wave with double amplitude. So constructive interference is when waves are perfectly in phase. Like here, for instance, right? You got the same phase here, and you got the same phase here, right? And the displacement, they add together, and the amplitude, now the amplitude is bigger, and the amplitude of the resultant is equal to sum of the amplitude of two waves. So now you have a bigger amplitude, you have a bigger wave here, because they were both in the same phase, so they added together, and now they're a bigger wave. So that's constructive, right? Now you got destructive interference, when two waves are out of displacement and they come together and they counteract each other. The amplitude of the resultant wave is the difference between the amplitude of an interactive wave. It can result in a lower amplitude wave, or no wave at all, because they're so out of phase, they kind of like oppose each other. And then zero amplitude, like I was saying, are when two waves are exactly 180 degrees out of phase. Wave traveling is basically traveling to a fixed boundary, and it's reflected and bounced back, and inverted two waves will interfere with each other. Next we have a standing wave. It occurs when two waves of the same frequency are moving in the opposite direction and interfere with each other. Next we have resonance, and resonance basically is an increase in the amplitude that occurs when periodic force is applied at natural resonant frequency of the object. So that means that objects vibrate more strongly when a force is applied to it at a certain frequency. They kind of vibrate more, resulting in a higher amplitude. So getting the right oscillation increases the amplitude high enough. Right? Now they have too much force. The force is increasing the amplitude higher. It's a bigger wave. Next we have the speed of the wave, which is equal to V equal B divided density, which is the measure of the medium resistance. So for instance, if sound is going through water, if it's going through a solid, if it's going through gas, right, that's the medium resistance. Speed of the sound is fastest in solid with low density and slowest in dense gases. Lower frequency of sound means that it's a lower pitch. Higher frequency of sound means it's higher pitch. And below 20 Hz is infrasonic speed, and above 20 Hz is ultrasonic waves. Next we have Doppler effect. So Doppler effect, I don't know if you watch Big Bang Theory, but as Sheldon was saying, Doppler effect is the change in pitch, for instance, of a siren or an ambulance or a police car as it passes by. It describes the difference between the actual and the perceived frequency of the sound when sound and sound detector move towards each other or away from each other. So it describes basically the difference between the observed and the source, what do you call it, sound. Right, so as I was saying, a siren, for instance, approaches observer, sound waves are compressed, resulting in a high frequency, or as siren as it moves away from the observer, sound waves are stretched, resulting in lower frequency and a lower pitch. So, if the perceived frequency, is higher than the actual frequency is when sound is moving toward each other. So, let's say you have an observer. So this is a person, let's call him John. John is just standing, and then boom, a ambulance comes and passes by him and kind of approaches John at a certain point in time, and then as a let's say the source or the sound of the source is 200 Hertz. All right, but the more a approaches a stable or like a person that is not moving like John, it's going towards him. Okay, the perceived sound from the siren is increased, right? So what John hears is actually not 200 Hertz. He hears like 300 Hertz, for instance, right? So it moves more towards him, and the sound is compressed, and it's a higher frequency and higher pitch. Alright, and then it's also like it sounds higher than it actually is. But then, like we said, John is just sitting, chilling, and then the what do you call it? The ambulance passes by. Now it's moving away from him, and he's just, just chilling. So as it moves away from him, the what do you call it? The sound wavelengths get longer, and they have now lower frequency and lower pitch, and now he can't really hear the pitch anymore as it moves away from him. The sounds get lower, and like we said, the sound, let's say from the siren is 200 Hertz. Now he hears like 100 Hertz because it's moving away from him. So this can be explained in this equation. So the perceived the sound is equal to the actual frequency, and then you have here the V is the source of speed, the speed of sound, plus or minus the detector speed, which is the observer, divided the speed of sound, plus or minus the source of speed. So let's discuss this. So as the objects move toward each other, all right, the observed sound, or the person observing, or the thing, or the group of people observing, is going to increase. All right, so it's going to increase. So let's say source is moving towards John. All right, so the source is moving towards a stable John. It's going to be a negative, all right, as the source of speed it's moving towards John, it's going to be negative, right? And then now we got the opposite of that, which is let's say the object is stable and the object is not moving. Now John is moving away from it. That's negative, right? Well, what if the object is stable and then John wants to move closer to it to see what's happening, right? So it's gonna be positive. So John is gonna move towards the object to see what's happening. All right, and then but what if the source wants to move away from John? So the source moving away from John is going to be positive, right? And the closer objects get to each other, the increased observer frequency. Next we have loudness. Loudness is the way we perceive the intensity of the sound. And then intensity average is rate of energy transfer across and then divided area across surface. Sound level is equal to 10 log times 1 divided IO in decibels, and IO is 10 to the power of negative 12, and that's the threshold of hearing. Alright, that's current, and that's divided IO. Attenuation is a repeated linear motion that is subjective to non-constructive forces. Non-constructive forces cause the system to decrease in amplitude during oscillation. Next we have beat frequency. Beat frequency is produced by interference between like two sound waves with frequencies f1 and f2, and they close in pitch. So f beat, for instance, 442 hertz minus 440 hertz is equal to hertz. So when two sounds are kind of slightly different frequencies played simultaneously, they interfere with each other, right? And that's what f beat is. Nodes are places with no displacement, such as these dots. You see these dots? That's a node, right? That's a node here. That's a node, right? So strings, we're gonna speak about the guitar strings. Strings are immobile and considered nodes, right? So the wavelength is equal to 2L, the length divided n, and n is a positive integer called harmonic. It's the frequency of vibrating object. You know, how many times it vibrates, alright? So the first harmonic is the longest wavelength, and it's 2 times L divided 1. There is one positive integer, alright? And then second harmonic is 2 times L divided 2 integers. Third harmonic is 2 times L divided 3. Fourth harmonic is 2 times L divided 4, etc., etc. Right? But second harmonic is half wavelength and twice the frequency. Third harmonic is 3 times the frequency. And we also have this at open pipes and closed pipes. So with open pipes, the ends of both pipes are open, allowing for air to move freely in and out. The fundamental frequency of an open pipe occurs when the pipe is at maximum displacement and both ends are points of maximum pressure. This means the wavelength of the fundamental frequency in the pipe is twice the length of the pipe, right? So hence 2L. And the harmonics are all odd numbered, right? So the first harmonic, for instance, is 1. The second harmonic is times 3, and third harmonic is times 5, and etc., etc. Okay. In a closed pipe, though, one end of the pipe is open, one end is closed. When air vibrates in the closed pipe, the node forms at the closed end, okay, and the antidote forms at the open end. This means that the wavelength of the fundamental frequency is 4 times the length of the pipe, hence 4L. Alright, and then for instance, there are an even number. So for instance, first harmonic is 1 time, second harmonic times 2, third harmonic is times 4, etc., etc. And that's it for sounds and waves. If you have any questions, let me know, and as well, have a blessed day.